Hi, my name is Mike Johnson. I'm the president at Advanced Machine Reliability Resources Incorporated. We're about to take a look at an application called the LubeCoach PC. This is a device that we created to help our customers build precision lubrication work practices, particularly focusing on grease replenishment and critical element bearings and electric motors and other mechanical machines. Given that machine lubrication is the single most important thing that you can do to support overall mechanical health of your rotating machines, I hope that you find value in this. I encourage you to take a good hard look, see if it might apply to your own efforts as you build precision lubrication plans, and I look forward to receiving your comments either by email or through phone call. Thank you much for your time.
First, a little bit about the company. AMRRI stands for Advanced Machine Reliability Resources Incorporated. AMRRI is a company that focuses on helping our customers improve machine reliability, typically Fortune 1000 sized manufacturers, typically process industries. There's 4 broad component types that we bring to the table: fluid forensics, lubricant condition monitoring services, component solutions, which includes the development of technologies such as I'm about to show you, provision of training material for certification and simple qualification for lubrication technicians, development of work practices, and simple problem solving of particularly challenging, vexing issues. We also have the means to provide labor for the work of machine lubrication and management for the work of machine lubrication when called upon to do so. Let's talk a little bit about the really big picture. In order for our lubricated parts, and for that matter, all of our rotating machines to enjoy the maximum productivity and life cycle potential of the lubricated parts, we need to be able to assure a continuous coating of lubricant that cushions and seals components to prevent wear and corrosion. In short, we need a clean, dry, continuously supplied, perpetually healthy machine lubricating film, whether we're supplying oil or grease to the machine, in order to avoid loss of component life cycle, such as we see in this example. If we aren't able to provide that clean, dry, productive film, then we suffer scheduled repairs and unscheduled repairs, which produce loss of productive time. It doesn't matter whether the repair is scheduled or not. If we're replacing lubricated parts, we need more from our machine lubrication program. Loss of lubricated parts produces problems with quality control through lost machine repeatability. Certainly, if we are doing unscheduled repairs, statistics tell us that we have an increased risk of injury, and particularly when the unscheduled repairs are urgent or emergency repairs. It produces a higher cost of production per ton. Ultimately, all of these things lead to lost competitive position for our company. And as tough as life is today in the manufacturing and maintenance world, it's not going to get easier. And the machine lubrication work process and work practice is often a source of undiscovered benefit for the whole machine reliability effort that we have. The folks that make our components tell us straight up that there's a substantial connection between the effectiveness of our lubrication program and the life cycle of our parts. Here's an SKF representation where in their chart, one of their bearing lubrication manuals suggests that 57% of the time when bearings fail prematurely, the lubrication issues are involved through inadequate lubrication, contamination, and surface degradation or surface wear. The surface wear corresponds to the lubricant's inherent capacity to protect machine surfaces. Now, this slice of the pie suggests to us that we don't really have a substantial problem with lubricant capability. We do have a problem with how we go about managing, applying, and reapplying the lubricant. In fact, inducing contamination and just presenting overall inadequate conditions. So we don't really have a lubricant problem per se. We have a lubrication practice challenge. So let's go through the process one might follow to come up with what represents a very high quality lubrication plan for element bearings. And we're going to pick on electric motor bearings here because electric motor bearings are particularly challenging to us, and people are prone to look for any kind of improvement. And since they're element bearings most of the time, this will correspond pretty well. So let's talk about electric motors for just a moment. If we approach the motor, look at the nameplate, we will often see on that nameplate the details that we need to identify the bearing type and size, and certainly, of course, we also need the bearing's operating speed, rotating shaft speed. This number that we see here, the 6308 UU, that represents a ISO or DIN designation for the LS or load side bearing. 6208 represents the designation for the other side or opposite side bearing. The 63 designation tells us it's a beefier bearing close to the coupling. The 62 designation tells us it's a smaller or less beefy bearing, same shaft size, same OD, but not as much metal, located on the shaft further away from the coupling. So with that as a starting point, we have a lot of information already we need in order to be able to come up with a very high quality lubrication plan for this particular motor. Some of the older motors that we work with have a different style bearing designation, super secret Dick Tracy code. This designation is the Anti-Friction Bearing Manufacturers Association, AFBMA designation. And you see a link here on the page. You can type that into your browser and dig a little bit more if you have an interest in looking at some more of the details. Needless to say, we also, with this designation, have a lot of information that we need in order to make good decision. 45 BCO for the drive or lower bearing, 35 BCO for the other side, so coupling side and other side. 45 represents the bore dimension, 35 represents the bore dimension. The side closest to the coupling, once again, gets a beefier bearing. The other information we see here, 03 and 02 represent the size or the design of the bearing. 03 is a more robust bearing, once again, and JPP3 represents the cage and or shielding design. So lots of information buried in that number there. So the first question we have to ask ourselves when we're looking at an element bearing and we're holding a grease gun is, should we be lubricating this bearing with grease? Clearly, there is a speed parameter which tells us it's okay for lubricating with oil and a much lower speed where it's okay for lubricating with grease. The speed parameter bearing manufacturers refer to as the NDM value. The NDM value speed limit, if you will, differs for bearing designs. Ball bearings have higher speed limits than thrust, ball, and roller bearings. Spherical roller bearings have higher speed limits by just a slight degree than thrust, ball, and roller bearings. So we've got to ask the question, is it okay to lubricate this bearing with grease? And if not, we need to lubricate with oil. We needed to make a determination what our speed is, and that is a function of the bearing type, size, and rotating speed. So step one is to calculate the speed limit to find out if it's okay to lubricate the bearing with grease. And you would think intuitively that a machine designer would not send us a grease bearing with instruction to replace grease if in fact it's not okay. Regrettably, that's just not the case. So it's pretty simple to figure this out. The NDM value is that bearing's shaft speed times the sum of the bearing ID plus the OD divided by 2. Now you could say this NDM value is the same thing as the pitch line velocity. That's a fair representation. We need to plug in the numbers and come up with the details. So back to the bearings that we first looked at, the 62 series bearings. It was 6208 if you recall. Looking up the bore and the OD dimensions for that bearing, and looking at the nameplate information to see the shaft speed, we have 1745 times the bore, the ID, plus the OD divided by 2, or 120 divided by 2, or 1745 times 60, and our NDM value, speed limit value for the smaller bearing, is 104,600. The larger bearing on that first motor we looked at, slightly different parameters. Again, the bore is the same, the OD is slightly bigger because it's a larger, a beefier bearing. Follow the logic, 130 divided by 2, so we have 1745 times 65, 113,425. So we have just determined the NDM value for these bearings. We compare these bearings, which are ball bearings, to the chart. Any number less than 340,000 is okay for grease lubrication. And I'm going to deviate from the normally scheduled program here for just a moment. It is fair to say that there are specialty grease manufacturers that do produce greases capable of NDM values or speed limit values approaching 1 million. But our rank and file products don't give us that luxury. So, step 1, calculate your NDM value. Step 2, compare to the general parameter, the speed limit parameters we see. Here's a chart that's useful for that. And determine, is it okay to lubricate with grease? And if not, is it okay to lubricate with oil? And if not, we're really talking about mist, then that's a specialized application. Step 3, once we have decided it is okay to lubricate with grease or oil, it doesn't matter which, we now have to determine what oil thickness we need once the bearing is up to normal operating speed and normal operating temperature. So in order to do so, we can always go to the bearing manufacturer's lubrication book, pull out a chart that looks like this, where we find the bearing's mean diameter, DM, on the bottom axis, and the bearing's shaft speed, which is, in this instance, 1745, the vertical axis. And where DM intersects with shaft speed, we have a drop-dead viscosity grade. So that's one way to go about determining it, or we can be more specific and calculate the minimum viscosity. The formula, which is really pretty straightforward, 27,878 times shaft speed to the negative 0.7114 power times the bearing's mean diameter to the negative 0.52 power. That works out to give us a bottom line viscosity, a minimum allowable viscosity. Whatever number we calculate or estimate, we take that and multiply it by 3 in order to come up with the ideal viscosity. So if we happen to guess that it's 12, 12 times 3 is 36. So we want to pick a lubricant such that once the oil in the grease, or once the oil in the oil gets to normal operating temperature, we still have at least 36 centistokes. So once again, let's apply this logic to our first motor example. We're going to calculate the minimum viscosity. 1745 was the speed, and DM was 60. So we plug the numbers in, do the calculations, and we come up with the minimum allowable viscosity of 16.3836, or rounded to 16.4. Multiply this value times 3, and we have a target viscosity of 50 centistokes for the opposite side bearing. For the load side bearing, we're going to come up with a very similar number, and for the sake of abbreviating this presentation, we're going to say it's close enough. In both instances, we're looking for a grease that gives us at least 49 centistokes once we're at normal operating temperature. Well, the next question is, for the product that we have in our grease gun, what is the actual viscosity at actual operating temperature? So let's say we're using a Chevron SRI electric motor grease, which happens to be a premium quality product, a very good quality product. If that element bearing, that motor, is operating at 50 degrees C, which is equivalent to 122 Fahrenheit, And we're looking at the oil viscosity in that SRI grease, which is 110, if I recall. So we call it an iso viscosity grade of 100. At 50 degrees C, where that temperature line bumps into the viscosity line, we drop straight to the bottom, and we see that our equivalent viscosity at operating temperature is 60 centistokes. Back one page, we saw that we wanted 49 or at least 50. All right, so we determined that yes, indeed, not only are we above 49, we're really in a very, very good product selection for this particular electric motor. The best fit that we could hope for would be a viscosity that is somewhere between 2 and 3 times the lowest allowable limit, or the drop dead limit. Most electric motor greases have a baseline viscosity grade of 100 centistokes. That's by design. The working viscosity 122, 60 centistokes plus or minus tells us where we are. 16.4 centistokes times 3 is 49. 60 centistokes is just slightly above 49, but we would say that's good enough. Let's move forward. Next question is one of whether we wish to try to use an EP formulation. Well, this is a bit of a busy chart here, but the bottom line is anytime our actual viscosity is at least 1 times the drop dead limit or greater, then we don't really derive any value from the use of EP chemistries. This 1 times the required viscosity or greater is called the kappa value. And strictly speaking, it's the actual viscosity of the lubricant provided divided by the required viscosity grade. A score of 1 or better says don't use EP products. That is a good rule of thumb. The chemistry within the EP products actually does have a mildly corrosive effect, and anything you can do to avoid inducing corrosion is good. So as it turns out, our electric motor greases do not typically include EP attributes because we have made a good enough viscosity base oil selection such that they're not required. Well, that was step 5, EP product or not. Step 6, we need to determine what volume we need to apply to the bearing, and that is a function of the bearing size. The SKF formula is bearing width times the OD times the space factor, 0.005 if our dimensions are millimeters, or 0.114 if our dimensions are in inches. So going back to that very first motor again, the OS, or opposite side bearing, dimensions were 80 and 18, so 0.005 times 80 millimeters times 18 millimeters gives us 7.2 grams. The loaded side bearing was slightly beefier bearing, 0.005 times 90 millimeters times 23 millimeters, the width of the bearing, equals 10.2 grams. Once again, we can be very specific about the quantity of grease that we ought to be considering for replenishment purposes. It is wise to use volume meters when lubricating high-speed and or electric motor bearings. There's a few manufacturers of grease meters available in the market. It's wise to avoid the use of a grease gun that can produce a substantial amount of grease very quickly, particularly around electric motor lubrication. So with that background, let's take a look at this application called the LubeCoach. Now the LubeCoach is a tool built for the purpose of being very specific about what we need to do with grease replenishment. We have the means to either key values into the LubeCoach here or use a lookup table. Now if we have a user defined, then of course we got to plug in the values, which means we have to get a measure out and go physically measure the bearing. But in this instance, since the bearing number is represented on the motor, we'll just pick that off of a pick list here. So the motor was 6208. We're going to come right down the list here, and we're getting close. 6208. and success. So here are our dimensions. The bore was 40 millimeters, the OD was 80 millimeters, the width was 18 millimeters. We saw that previously. Here it is validated for us in our calculator. Just scooch that up a bit so we can all see it a little bit better. We need to plug in the shaft speed, 1745, and we need to plug in the actual bearing temperature, and let's say it's 50 degrees C. 50 degrees C. So we have a few operating conditions that need to be considered when setting a frequency for replenishment. Let's take a look at those in our PowerPoint presentation here. Now here's the formula used to determine the replacement interval. That formula has a operating environment parameter we'll refer to as K in this instance. K is the product of 6 factors multiplied together. Bearing temperature, housing factor, temperature that is greater than 100 but less than 150 would be a 0.9. We see that number posted here in the box. The higher the temperature, the smaller the discount factor, meaning the higher the temperature, the shorter the replenishment interval. Contamination factor, light non-abrasive dust, heavy non-abrasive dust, light abrasive or heavy abrasive dust, the more aggravating the atmospheric contaminant condition, the shorter the lubrication interval. Moisture factor, humidity below 80%, 80 to 90%, condensation on housing or water on the housing. The greater the water content, the shorter or the smaller the factor, and again, the shorter the replenishment interval. Vibration, and we're going to infer vibration means shock loading. Low shock loading, medium or high shock loading, the greater the shock loading, the shorter the replenishment interval. Shaft position, a horizontal position or horizontal axis is a factor of 1. Vertical axis is a factor of 5. Since we're fighting against gravity with the vertical axis, we should replenish more often. The bearing design, ball bearings factor is 1, cylindrical needle roller bearings 0.5, tapered spherical roller bearings and thrust bearings 0.1. All of these factors in the green boxes are multiplied together to produce K. The rest of the parameters within the calculation relate to the bearing itself. So with that in mind, let's come back over here to our LubeCoach and see how that is expressed. So we plugged in bearing temperature, 50 degrees C. Any temperature below 65 is given a default factor of 0.9. The contaminant load, let's say it is an element bearing operating in an environment where there's light, non-abrasive dust. You could argue that the bearings are well shielded. We don't really have a lot of dust, abrasive or non-abrasive dust contact that's possible. The same could be said for the moisture contact. So occasional water, occasional condensation, and we've got a few extra factors here for really, really high-end water contamination. But let's say that our humidity is between 80 and 90% instead of direct water contact on the motor bearing. Let's say the vibration load is relatively low, and we have a horizontal center line. And once again, let's say we're using Chevron SRI polyurea grease, very high quality electric motor bearing grease. Viscosity at 40 is about 110. 110. Viscosity at 100 degrees C, if I recall, is about 12. And that gives us information that we need to know about the grease that we picked, the interval, and the volume. And now we can go about determining when we need to go, what product we need to use, and how much we need to supply to the bearing. Now, Let's look at this for just a minute. Now we have a 471-day interval. That's a pretty long interval. At that interval, we're going to apply 7.2 grams of grease to the smaller bearing. And then if we actually calculate what's required for the larger of those two bearings, we're going to see that 6308 gives us 10.4 grams of grease. The same interval because the bearing is rotating at the same speed, but slightly more grease. Let's say hypothetically, this motor was pulled out, rebuilt, and then put in somewhere else. With a variable speed drive controller at 1200 RPM. So now the same bearing can be lubricated at a longer interval. If we have a motor the same size, turning at 3600 RPM, the same bearing now needs to be lubricated at a shorter interval. So these influences over here are pretty dramatic. Let's put this back to 1800 RPM. And now take a look at some of these influences. Let's say it's not a bearing buried inside of a motor housing, but rather a bearing on a pillow block supporting a shaft. Once again, it's a ball bearing, but now it's exposed to heavy abrasive dust. And let's say the same bearing is supporting a shaft on a conveyor that's outdoors, and we get occasional water on the housing. Of course, if it's on a conveyor, we won't be running at 1800 RPM. Let's call it 65 RPM. Our bearing temperature might remain the same. Let's leave vibration where it is. Let's leave the center line where it is. We've made a few changes here. We've reduced the speed. We've increased the contaminant load. We've increased the moisture load. All these parameters remain the same. But now, because we have a much lower shaft speed, we see that the calculated minimum allowable viscosity is much, much higher than it was previously when this was an electric motor bearing. The ideal viscosity range is 3 to 5 times the minimum allowable grade. If we're using that same electric motor grease to lubricate a pillow block bearing of the same size, turning at 65 RPM, we see that the viscosity is not nearly adequate enough to fulfill the minimum requirement. So this being the case, we have the wrong product picked, and we would see that straight up. So that's how LubeCoach works. Now, if we have keyed in this information and we want to save it, we can do so very easily. You can type my name, machine number, and inboard bearing, and save this information to a log where we now see Mike Johnson, the bearing, the machine, the bearings identified, the parts identified, the date, bearing parameters, operating conditions or influences, the calculations, and then the details about machine lubrication. And we can store as many of these calculations as we would like to store as time passes. If something changes around the machine's operation, we can come back to any one of these parameters, double click on it, restore the study, and we are back to looking at the details that we plugged in at some previous point in time. So this is how the LubeCoach works. With this information at hand, any reliability engineer would be able to provide very precise tasking for the volume and the frequency. This new work practice should be supported with the use of ultrasonic energy measurement. And while running these calculations, we can determine whether the lubricant that we have selected is in fact a good fit. Thank you much for your time. I hope this is useful information to you. If you have an interest in looking further at this, please don't hesitate to call. My name is Mike Johnson. My phone number is 615-513-3000. Have a good day.